And now we discuss electric potential energy.
Woo-hoo.
See, even my wife thinks that's very exciting. So let's get into this. And I'm going to describe this in terms of two parallel plates of charge. They have equal and opposite charge. And as we have already learned, the electric field produced by such plates is uniform. So the electric field between the plates, I say approximately uniform because in reality we usually don't have infinite plates but finite plates, and there's fringe effects on the edge, but we're not concerned about that for our discussion. So we'll have a constant force acting on a test charge that's anywhere in between those plates because the E field is uniform. So we put the charge there and we're going to allow it to move from A to B. If it's moved from A to B, work is required. Now work is required because it wants to, the positive wants to stay on the negative plate, right? Opposites attract. And so it's going to take some effort to move this charge from A to B. An external agent is going to have to do that work. So you can envision yourself grabbing it and moving it across. How much work do you have to do? Well, it's Ft cosine of theta as always, if you recall the work done by a force from our work energy theorem, or our work energy unit. And Ft cosine of theta is FED, namely the electric force, that's the F, times d cosine of theta is just d, because the angle between F and D is 0 in this case. And now the electric force is Q times E. So QE times D. QED. Okay. How can the amount of work change? Well, it's greater if any of these increase, namely the charge, if it's a bigger charge, a larger E field, or a greater distance. Simple as that, the three variables there. Now, what's happening to the electric potential energy? The electric potential energy as we move it along here. Well, if you're thinking of gravity, you're thinking well, because it's the same kind of idea. As we move this up, it has the potential to do work as it moves back down to position A, or flies back to position A. So we're increasing the potential energy as we move it across there, but not gravitational, the electric potential energy. Well, what work is the electric field doing on the test charge? Kind of like what work would gravity be doing in a gravitational field. The work from the E field on the charge is Ft cosine of theta, which is minus FED. Why? Because the electric field goes from top to bottom, but it's moving in the opposite direction. And so what that means is that Ft cosine of theta is actually negative. So we have minus Fe. Basically, the electric field force is in the opposite direction of the displacement. And so that's minus QED. So let's consider the electric field and what it's doing. Well, it's doing negative work on the charge that we just looked at as the potential energy of the charge increases. So if the potential energy is going up, it means that the electric force acting on the charge is resisting that displacement, kind of moving it against the force of the electric field. And that's kind of similar to something else we've looked at, isn't it? Indeed it is. And that particular kind of force that we've looked at was the force from G fields. So we're going to relate it more and more to G fields momentarily in our discussion of this rather abstract concept that we're dealing with here. And so we can say the following now, that the potential energy gained by the charge, if you're going to gain potential energy, is equal to the negative of the work done by the electric field. So if the electric field does work, Well, let's say it does positive work. It pushes the charge in a certain direction. Then the potential energy gained would be negative. So in other words, the potential energy goes down, which is the same thing as taking a ball and dropping it in a gravitational field. As gravity does positive work, the potential energy goes down. So it's really not that mysterious. It's really quite simple in principle. So this change in electric potential energy as the charge moves from A to B in the graphic we just looked at is as follows. So it's the work done by the electric field is UA minus UB, which is the negative of UB minus UA, which is really the change in potential energy, in this case gained. We gain it, and that's also the change. So that is minus delta U sub E. So work done by the electric field is minus change in electric potential energy. Same thing we have with gravity, okay? Let's look at the charge plates again, and let's consider when the charge is released from point B. Now, if it's released from B, it wants to depart the positive plate and zip down to the negative plate. So I've got it oriented right now to be very similar to the situation with a mass in a gravitational field. When it's released from point B, where it's at its greatest potential energy, the electric field pushes it down here and it loses potential energy. So it's going down. Potential energy is going down. The E field is doing what kind of work? Positive or negative? It would be positive because it's pushing it there. Now let's summarize some of these results. So at least in partial summary to what we've just been discussing, we can consider that the greatest amount of electric potential energy is at point B. And as the electric field moves this charge down, there's a loss in that potential energy. Well, how much is it? Well, it's equal to the amount of work done by the E field. The electric field does work, and that corresponds to the loss in potential energy. And that work is positive because it pushes it in the direction it's moving. So the positive work done by the E field is equal to the negative change in U sub E, the electric potential energy. And that is the potential energy at B minus A. Why? Because that's the beginning and the end. Now it changes final, that'd be A minus B, final minus initial. The negative of that is B minus A. So there you go. And it's greater at B than it is at A. So therefore, this quantity is greater than 0, which makes sense because the electric field is doing positive work. So the negative change is also positive. Now, that change in electric potential energy corresponds to an equal negative change in the kinetic, because these are non-massless particles that are being accelerated and therefore have some speed when it goes from B to A, and therefore total energy is conserved, as we would expect it to be. And now we're going to take a little break, and when we come back in the next video, we will discuss electric potential.